In this video, we're going to look at how reinforced learning works. So we've talked in previous videos about supervised learning, where we had our training and our testing data, and we had labeled information. We knew what class different groups of data belonged to. And we've looked at unsupervised learning, where we didn't have labels and we had to find clusters and groups. Well, reinforced learning is the third type of machine learning. With reinforced learning, we are looking at steps in a process and trying to find the best order to those steps. So let's take a look in this video about how reinforced learning works. Let's talk about the theory, and then the next couple videos we'll look at implementing that. All right, so we just talked about the difference between supervised and unsupervised, right? Supervised has trained and labeled data, and we predict a label. Unsupervised learning, we have unlabeled data, we're trying to identify groups. And reinforced learning, we're simulating an environment where agents interact with the environment and receive feedback. So we need to identify rewards for behavior, come up with the constraints for that behavior, and we're looking at the steps in the process. So we're trying to find the optimal sequence of actions. Now, when we do reinforced learning, we're doing structured problems. That is, we are assuming that the problem is well defined, that we can fully define the environment. And so reinforced learning is often used for like logistics, where we know we have, here's the different roads, here's the paths you can take. Or in manufacturing, here are the different steps to make something, do something, and we're simply about choosing the order that is more efficient. Okay, so it has to be a structured problem where the problem is well defined, we know the environment, which means we have to specify the procedures. What are the steps that can be taken to solve the problem? We know the rules, what can or cannot be done to solve the problem. We often hear stories about, right, artificial intelligence. They're given reinforced learning challenges, trying to figure out, how to win a game, and we find they cheat. The robot hand is supposed to pick up the ball and move it to a new location. Well, it finds if it just breaks, it resets the system, it automatically wins, or it just moves the table. It doesn't have to move the ball. So working outside of those limits, and that comes down to, did we not well define the rules about what can or can't be done to solve the problem? And then there are policies, general guidelines for making the decisions, how we prefer that what the solution looks like. And so when we look at these structured problems, we have procedures, we have rules, we have policies. When we do reinforced learning, we're using the Markov decision process. So you'll remember from our previous videos, we talked about Monte Carlo simulations. And so this is the same type of thing where we're iterating through a process. So when it comes to reinforced learning, we start with an agent, such as a delivery truck, and they have to take an action. Which location will it travel to next? Now, going to that location next instead of another location results in some kind of reward. For the delivery truck, there is revenue earned from dropping off materials at a location, and so we have a profit maximization problem where we're trying to make the most money we can by finding the route that allows for the most deliveries. We might also have a cost minimization problem where we're looking at the extra cost of having to go back and forth if it's not an efficient route. We have to travel long distances because we're not dropping off things that are nearby each other. That can have a high cost. So we are using that Markov decision process, and we're iterating through and looking at the scenarios in terms of how do we maximize the reward, but you have to have some kind of optimization, either maximize something or minimize something else. Now, in this case, when we look at the agent, the state of the agent will change. The delivery truck will go to the next location. It's now in a different location. It has a new decision to make as to which direction to go. So each time there's a change of state, there's a new decision to make. And then each time a decision needs to be made, there needs to be a consideration of what you're optimizing and the reward that you're getting. So in the Markov decision process, the agent is in some kind of environment, and it has to be a well-defined environment. So we would create a map or a grid as to where the agent could go. And so in this case here on the image on the right, what you see is that this agent has this environment, and the part my head is covering up is there's home base, and there are 3 different locations that the truck needs to go to make deliveries. Okay. So the agent has a goal they wish to optimize: lower cost, higher return, more profit, something they're trying to optimize. And they take an action. So in this case, they can move from home to location A. Each potential action has an associated probability of being selected. And so we can change the weights. Are they more likely to go one direction versus another? Or are they all equally likely? If that truck goes to location A, they receive a reward. And each potential reward has an associated probability of being earned, right? So each location has a different reward and a different probability attached to it. The action will change the state. The truck is no longer at home. The truck is now at location A. And so in this new environment, then the agent still has that goal to optimize something. And so then we'll take the next action. That next action has an associated probability with being selected and a reward if it is. And so we move through. When we iterate through, you can see here on this visual, is that you start with time t, and then you go t plus 1, t plus 2 as we iterate through the process. Now, the assumption, right, is that the environment is well defined. We call it the fact that the environment is discrete. So when we say an environment is discrete, it's because all possible states are known. So in this particular case, the truck can only go home, A, B, and C, and the routes are defined. So if they're at A, they can only go home, C, or B. And if they're at C, they can only go to home, A, or B. So let's look at an example here. The delivery truck starts the factory labeled home, and at time 0, because in Python we start counting at 0, the delivery truck wants to optimize their profits. So suppose going to location A returns a profit of $10,000, while location C returns a profit of $15,000. The delivery truck takes an action. It could choose, for example, to go to location C. That truck now is at location C. We've now had a change of state, and we're now at a new time. We're now at time 1. It receives a reward for dropping off the materials at location C, and then because it wants to optimize profits, it's going to have to choose a new location to go to. It can go to home, A, or B. It looks at the profits for those different locations. It takes an action. And so we move throughout this environment. And we keep repeating that, right, as we move through time. And the delivery truck will continue this loop of receiving a reward after they drop off supplies until all the deliveries are made. So the reinforced learning algorithm is attempting to find a route that provides the most profit, recognizing that longer travel distances have more costs, and it's exploring the routes on the map and learning. Now, when it comes to learning, there are different types of reinforced learning algorithms. The brute force Monte Carlo method just goes through and tries all different combinations, and so looks at all the different routes, tries all the different routes, and does it brute force, right? Tries it all, and then considers the reward, and then looks at which one was the best route. It's only considering the reward for the current action, so it's really not anticipating future rewards. Is very much living in just the present, and it is just going different directions ultimately to see which way turned out to be the best after the fact. There are 2 other methods for reinforced learning, one called Q-learning and one called SARSA, or State Action Reward State Action. So Q-learning considers rewards from both the current action, so I'm going to go to location A, what do I get in terms of dropping off the deliveries at location A, and it attempts to understand future possible rewards from the actions that will come after the current action. So if I go from home to A, I get my reward in A, then what are the future routes I could take? I could go to B and get this reward. I could go to C and get this reward. I could go back home and get nothing. So it's trying to look at what is not just the reward right now, but what's the reward from the actions that will come after the current action. So it creates what's called a Q function, and a Q function is the expected value of those combined rewards, the rewards from the current action and the rewards from the anticipated actions in the future. When we look at Q learning, we have a learning rate. So our Q, that expected value of the combined rewards, is going to be weighted based on how much of the expected value is the past information versus the new information. So how much are we learning? The larger alpha puts more weight on the future. Okay, lower alpha considers just that past information. We look at what's called temporal difference learning. So we're updating the algorithm, and we can use a convolution neural network, and that is the neural networks that we're going to talk about in some other videos. And we have some kind of metric to measure how well we are learning, and here it could be to minimize the mean squared error. When it comes to Q learning is called off-policy learning. Off-policy learning is that we estimate that future Q based on the ideal conditions. So we're looking at Q in terms of the maximum possible reward at any given state. This is compared to SARSA, where SARSA is what is called on-policy learning. With on-policy learning, it's the estimated future Q is the total rewards based on the policy it follows. So it is what the algorithm recommends rather than the ideal. And so remember, when we talk about policy, we're talking about general guidelines for making decisions. And so we're actually going to look in the next couple videos how you build a Q learning model, a SARSA model, and how these off-policy and on-policy learning methods are different in terms of the actual code and the math. So we're going to do that using what is called a frozen lake example. I'm just going to move my face. So what we're going to do is we're going to start with a grid, and we have our person, our player here, who needs to get to the finish line, the end of the race here, and they can move right, left, up, down on the grid. But the key here is you don't want to fall into the lake. And so there are these holes in the lake that we have to consider. So we're going to try to find what is the best route to get to the finish line without falling into the lake, falling into a hole in the lake. So in our next couple videos, what we're going to do is we're going to solve this problem here and see how well we can solve this problem using a brute force method, a Q learning method, and with SARSA.